My name's Hannah Isla. I'm the Geology Program Manager here at Tellus, and we're so glad you guys could all join us this evening for this chat about forever chemicals in the Coosa River with Jesse. But before we get started with that, just a couple of reminders about some stuff that we've got coming up. If you're here tonight, if you're one of our members, if you have seen our Swap Timber initiative in the past, where we partner with other informal institutions and other cultural centers around Metro Atlanta, that is coming back for the month of September. So you're going to be able to get a lot of use out of your membership, not just at Tellus, and there'll be more information coming up on that really soon. Our next activity happening that you can come see us for in August is our Lunch and Learn on August the 30th. It's going to be about Morse code with Bob Finger, one of our educators here at Tellus. So come see us for that. And then if you want to look out to something else fun to do on a Friday evening, or is it on a Saturday evening? Is the 29th is a Friday, right? Yeah, it's a Friday. If you want to do something else fun on a Friday night that's not Science Friday night, not our SciFri, our Science Comedy Night will be on September 29th. So you can look at the website for more information about that and to get tickets. That'll be a fun night. Last year's was quite fun, so it should be another good evening for that. We'd also like to go ahead and thank our sponsors for this evening, which is Q102. So that we can keep bringing really awesome content like tonight's lecture to you. So we are joined tonight by Jesse Demonbreun-Chapman from the CBRI, the Coosa River Basin Initiative. Jesse joined CRBI in December 2016 as the Executive Director and Riverkeeper. He previously worked at the Ogeechee Riverkeeper based in Savannah, where he served as the organization's outreach coordinator. Prior to moving to Savannah, Jesse worked for a refugee resettlement agency in Stone Mountain, served as the director at the Boys and Girls Clubs of Northwest Georgia for 4 years, and also served for a short time on the CRBI Board of Directors. He's a 2008 graduate of Berry College, where he studied biology and English. He lives in Rome with his wife Ashley, daughter Liana, and son Felix. In free time, if any of us actually have free time, which I totally understand, he loves to go mountain biking. So, Jesse, thank you so much for coming tonight. We're so excited to hear from you.
Well, thank you all for having me. I'm really excited to get to give this lecture in a museum that my family and I really cherish as a gem in this region, really in the state. I love that it's so close by. So thank you all for joining. I'm going to give just a quick, fast and dirty overview of who CRBI is before jumping straight into the topic. We are celebrating our 30th year this year, which is really exciting for us. I feel like that's pretty impressive for any nonprofit. And our entire program kind of falls underneath these 4 program areas. We go about the protection of the Upper Coosa Basin with a really holistic approach, where we advocate for better results both at the Capitol during the legislative session and specifically related to pollutants of concern, like we're going to talk about this evening. Education programs, all kinds of different water monitoring, both for our own trend analysis, also for public outreach, and restoration projects. So we partner with a lot of different groups, particularly in the Conasauga Basin, to help restore water quality, habitat quality, particularly focused around protecting endangered species, which we have a lot of in this basin. So I wanted to show just kind of a quick map that demonstrates we stay pretty busy and on the move. The basin that we cover stretches west into Alabama around Weiss Lake. It stretches east practically to Lake Lanier, just past Dawsonville, and north we cross just a little bit over the state line into Tennessee as the Conasauga kind of snakes north into Tennessee and then comes back down into Georgia. And when I talked about those restoration projects, that purple basin up at the top of the map, that's the Conasauga. That's where a lot of our endemic species are found. So species that are found in that basin and nowhere else on the planet. In fact, that river basin, it's a pretty small river, has more biodiversity, has more aquatic species in it than all of the rivers in Europe combined. So we work on a really special basin. I feel really honored to get to work to protect it and to spread the word about all the cool different things that we have going on. One of our outreach projects underneath water monitoring impacts some areas locally, and it is Swim Guide. So if you or any family members or friends enjoy getting on the water, we do weekly bacterial monitoring at popular recreation sites, boat ramps. You'll see here, these are around Lake Allatoona, all of the boat ramps kind of on the rivers in between Allatoona and Weiss Lake. We run this program from Memorial Day to Labor Day with the help of a wonderfully talented group of interns. And so if you know of any college students, in your life that are looking for summer projects and need an internship, we start looking for our summer interns beginning in February and March, and those slots tend to be pretty competitive. But we have a wonderful team. If you are interested in seeing these, we're sampling specifically for E. coli to let people know where it might be a little bit more hazardous to swim in terms of public health. Those results get posted on our website every Friday by noon at coosa.org. And then you can also download, there is a Swim Guide app that has sites where sampling has taken place across the globe, and we're an affiliate. But the reason why I came here is to talk about everyone's favorite emerging contaminant, PFAS. So I trust that most everybody has either heard of the term PFAS or forever chemicals, which is frequently kind of just a colloquial stand-in these days for PFAS. And so what is a PFAS? Well, I took a picture of one in the wild. That's not a picture. This is a tiny molecule that is invisible. It doesn't give a smell, and so identifying these in water resources is actually really challenging. And if you are feeling like this story kind of came out of nowhere and now is everywhere, part of that is because the technology required to find these chemicals in as small of a concentration as we need to find them didn't exist until quite recently. A few years back, we were doing some sampling work, and we wanted to see a list of total PFAS in a sample, and there was only one lab in the entire planet that could do that, and it was in Australia. Now that's not the only lab. The technology is advancing. A lot of things are advancing, but this is why this issue seems to have kind of come out of nowhere. But what is PFAS? So PFAS stands for per and polyfluoroalkyl substances. It's a mouthful. Basically, you have a carbon chain, an alkyl chain that's been fluorinated. That alkyl-fluorine bond is extremely strong and very durable. So the term forever chemical doesn't mean anything. It's not a scientific term. It's basically just a term that has kind of stood in for a number of chemicals that persist in the environment. They don't break down easily or much at all. And this is one of those because of that bond. Because of the strength of that bond, these chemicals have found their way into an enormous amount of applications. And so the first PFAS was discovered by accident in a lab in 1938 by a young scientist then working for DuPont, studying different gases associated with their Freon product. And while running an experiment in a lab in New Jersey, he realized that the experiment was malfunctioning because of a waxy substance that had built up on one of the nozzles that was supposed to be releasing gas. He scraped a bit of that off. DuPont studied that chemical for the next 10 years, and then the world got Teflon. That was the first kind of commercial application of a PFAS out in the wild. The next, over the next couple of decades, 3M also started producing PFAS. The world got Scotchgard. And then the next kind of major widespread use of PFAS came with firefighting foam. For many fires, specifically chemical fires, fuel fires, water is not a very effective flame retardant. So they had developed different types of foams, and the first one that used PFAS, I believe, was developed in 1964, but it didn't enter widespread use until 1967 because of a catastrophic naval disaster. So the USS Forrestal was a Navy vessel outside of Vietnam, and a power surge caused a weapons malfunction on deck. The ship burned overnight. That fire caused a fuel tank to explode, which then set off several other bombs on board. It was an unmitigated disaster. They were not able to control the fire. It just got worse and worse, and they lost over 130 sailors in that disaster. As a result, the Department of Defense then essentially required that PFAS-laced firefighting foam was a required staple on any vessel at sea. That firefighting foam was typically, you'll see it referenced as AFFF, aqueous film forming foam. And the idea is it's a film that will smother a fire, will starve it of oxygen, whereas water might just kind of push the fuel and the chemicals around. Fuel floats back to the surface and reignites. That's why it's not effective. But that film-forming foam smothers the fire. It's very effective. Fast forward the next few decades, really PFAS took off. So originally you had 2 or 3 main kind of flavors of PFAS out in industrial use. And slowly, beginning as early as the 50s, it started to become apparent that there was a risk of toxicity related to these. And manufacturers started creating lots of different variants of those original. They tried to shorten that chain. So the original kind of PFAS, and this is an example of PFOA, these were frequently called C8 because of that 8 carbon chain. Well, then we started to see the introduction of C6, with the idea being that perhaps the shorter chain PFAS would not persist in people's bodies as long, would not have as toxic an impact, and they were frequently, marketed as the safer alternative. Well, more and more research recently has shown that hasn't panned out. While some of the newer PFAS do vary in terms of how long they reside in our bodies, toxicity levels are generally the same as those original chemicals that were used. But with the explosion of the diversity of these chemicals, their use and application just went everywhere. And when you think about it, anytime you're trying to give a particular fabric, substance, a different characteristic, it's helpful to have an extremely durable molecular bond. So if you've ever went out and bought a cheap rain jacket, after a couple of years, it won't keep you dry anymore. The fabric soaks through. If you buy a very expensive rain jacket, it will last a lot longer, and it has much stronger PFAS. The PFAS is the chemical that gives that rain jacket the durable water repellent characteristic because these chemicals are hydrophobic. It found its way in Easy Glide dental floss. It found its way in nail polish, eye makeup, lots of food containers. So candy wrappers, fast food wrappers, pizza boxes. Essentially, anytime you had paper holding greasy food and the paper didn't fall apart, if it wasn't wax paper, it was probably PFAS. So like many chemical solutions that we've discovered, we have just really put them into essentially any and every industrial manufacturing process that we can, and now are realizing after we've covered the globe in this substance that it wasn't a great idea. It's a little troubling. I promise this whole talk won't be a complete bummer. this will continue. We're going to get some hope at the end. One of the problems with PFAS is they're incredibly difficult to grab hold of and then get rid of. All right, so it's very difficult to break them down because of the durability of that bond. And they're very tricky to grab hold of. So we have this, instead of the lovely water cycle, there's the PFAS cycle. I'm not going to read all of this. But essentially, think about our conventional wastewater treatment methods that we use as a toddler who has a plate of spaghetti, right? You can hand that toddler a dish rag if a little bit has spilled off of their plate. The result will be that toddler will just smear that sauce. It's just going to move it around. It's going to end up in the toddler's hair. It's going to end up everywhere else, right? You're not going to clean it up. Essentially, our treatment methods have done that with PFAS. The technologies that we have used for generations that work very well on conventional pollutants have actually advanced the spread of this chemical far and wide. And so some of the ways that work is our wastewater treatment systems have discharge sometimes. So like the water has gone through the treatment plant and it goes back to the river. That discharge will have PFAS in it because the conventional methods didn't work. Some wastewater treatment plants apply their wastewater, instead of going directly to the river, to a land application system. So they spray it over the land with the hopes that the land will sequester those pollutants. It'll get taken up in the plants. It will, be held in the soil and break down over time. Well, that either. And so those land application sites have contaminated groundwater, contaminated wildlife, and every time it rains, the runoff is contaminated. All right, so wastewater treatment plants, as they treat wastewater, they also remove solids. We call those biosolids. So it's anything that gets sent down the drain, gets dewatered, which doesn't remove all moisture, and can be handled in a handful of ways. You can, again, land apply. Lost it. There it is. Biosolids can be applied to a field to grow hay for DOT projects. But again, those biosolids are contaminated with PFAS. Those fields that have biosolids with PFAS then contaminate the groundwater and the runoff. If you decide, okay, we're not going to contaminate the fields, we're going to send our biosolids to a landfill. Well, that causes two other problems. Biosolids do have a lot of high moisture content, and most landfills were not designed to contain a lot of high moisture content waste, so you see things like slope failure when they take on too many biosolids. We've actually had a couple of those on the Etowah River, which releases the Etowah River, which has PFAS in it. And those landfill systems themselves have leachate collection systems. So as fluid percolates through the landfill and comes out the bottom, they have a system that collects that wastewater. They containerize that wastewater and to a wastewater treatment plant. So they send it right back to where we began, but somewhere else, somebody else's wastewater treatment plant. So now that wastewater treatment plant is getting wastewater laced with PFAS. They're contaminating their biosolids, their discharge, and the cycle goes on and on. So the reason why this problem is so persistent, the reason why you're seeing articles that say, it's in everyone's blood, it's in half of drinking water systems today, is because of this. This is a difficult emerging pollutant for us to control. Beyond how the pollutant moves around, there are a number of health concerns associated with PFAS. Several things related to increased risks of cancer, kidney and liver disease, reproductive issues, early birth, low birth rate, hormonal disruptions, reduced immune response. So PFAS concentration in the blood can directly be linked to reduced performance of vaccines, because the whole point of a vaccine is to help your immune system kick into high gear when it sees, a pathogen. Well, if you're impacting the immune system's response time, you're impacting the effectiveness of those vaccines. And as I mentioned, there are a ton of these. So we started out with, 3 different kind of marketable PFAS, where now there's somewhere in the range of 5,000 and 10,000, all under proprietary names. We don't even know the molecular structure of most of them, and almost none of them have been vigorously studied other than those originals. So there's a whole host of public health issues that we don't know because they've been developed so rapidly, we haven't had the time to put them through peer-reviewed analysis on community scale. Now, I do want to give a caveat here, again, going back to the idea of this nowhere. We are currently living with the impact of these elevated health risks. It's not like tomorrow everybody's going to start getting kidney and liver disease, higher rates of cancer. When we see the rates of cancer across our society slowly elevate over time, this is one of the factors that have contributed to that. So I want to make sure and reiterate, I'm not up here saying the sky is falling. We're not all doomed, tomorrow because of this impact today. We've been living with it. So the slow rate at which our communities have become a little sicker, this is one environmental contributing factor to that over time. But that also gives us hope to reverse course as we develop new technologies that can address it on an environmental scale. Some federal updates. So the federal government has really not dealt with PFAS at all until after the year 2000, essentially. They worked with companies to voluntarily phase out some of those early longer chain PFAS in the mid-2000s, but things have really heated up over the last 7 years or so. In 2016 was the first health advisories for PFOA and PFOS, and in 2022, just last year, they drastically reduced the health advisories for those 2 chemicals and added 4 others to that health advisory. Just recently, either at the end of 22 or early in 23, they introduced the idea of CERCLA designation for PFOA and PFOS, and that's commonly known as Superfund. So this is a hazardous designation for these chemicals and sites that are contaminated with them. And then just recently, EPA introduced maximum contaminant levels, so enforceable limits on drinking water for PFOA, PFOS, and 4 others. I do want to take a minute. I'm not going to go through all of the numbers, all of the different limits, but I want to talk for a moment about how small volumes we're talking about. So the health advisories, anytime we're talking about PFAS, generally we refer to measurements in parts per trillion. You can think of parts per trillion as a kind of fraction. So if you had 1 trillion molecules, one of those trillion molecules is the thing that you're looking for, right? So the health advisories for PFOS and PFOA, PFOS had a health advisory of 0.02 parts per trillion. PFOA had a health advisory of 0.004 parts per trillion. That is a lifetime exposure advisory, and it is meant to be protective of the most vulnerable in our population. So that's not a health advisory that's built on the healthiest. It's meant for infants, nursing mothers, people who are immunocompromised. It's meant to be protective. So above that rate, they're basically saying they can't guarantee that the most fragile amongst us are safe from public health harm from these chemicals. So I want to take just 0.004 parts per trillion and try and put that in perspective. So we're going to do it with the distance between Earth and Sun. The maximum distance when we are the furthest away from the Sun is about 94.5 million miles. All right? 1 So if we were to break that up and say 0.004 parts per trillion, that fraction of that distance, it would be the equivalent of moving a 0.5 millimeter closer to the sun. We are talking like unthinkably small quantities. When we get to the idea of the actual enforceable limits that they're hoping to set, what they're proposing now is 4 parts per trillion. Again, putting that 4 parts per trillion across this distance is the equivalent of 2 feet. And so when I go back to this is all happening now, part of that is because, again, technologically, we couldn't find concentrations this small until very recently. And again, kind of drives home the troubling nature of how prevalent it is everywhere because of the things that we've done to put it across the environment. So we're going to start getting some glimmer of hope. So I'll go back to here. We've got CERCLA, Superfund designation, drinking water standards. If you're looking for hope in those actions, don't. Not anytime soon. If anybody has followed any action that EPA has taken in the last decade, it's going to be mired in lawsuits for some time. So it is really great that EPA is tackling this very important topic, but we shouldn't assume that we're actually going to get relief on the ground anytime soon because of federal action. Now, states can sometimes go unnoticed, and their laws can get challenged, but they don't typically get challenged quite as vigorously as federal laws, and some start to get into state codes. So instead of public health, we're going to start talking about economics now. A handful of states have started introducing PFAS bans on food packaging, PFAS bans in California in textiles and cosmetics. Georgia even has a sort of PFAS ban specifically related to firefighting foam. It can't be used in training anymore. It can still be used in an emergency, but it can't be used in training. So while EPA is going to be caught in courtrooms for years to come, these laws are starting to go into effect, some as early as this year. And any company that intends to do business across the entire country is already trying to figure out reformulation. They're trying to figure out how can we make our product without any PFAS in it. Because if you are a large, multinational company, you can't cede California to your competition. You can't just give up that market share. Right? That would be a horrible business decision. So while the federal guidelines might not have a short-term effect, these state laws absolutely are. They're actually going at, potential profit margins for companies, which is a really great incentive to invest in research and development to find a way out of PFAS. So while I'm encouraged by what the federal government is doing, these are the things that actually excite me in terms of what could impact the way these companies use these chemicals on the ground. We'll get into the reason why I care about this subject so much. So she mentioned earlier, my background is in biology and English. I am not a chemist, and I don't work in an industrial manufacturing setting. But the reason why I care so deeply about this is because of this heat map. So we participated in a nationwide study with the Waterkeeper Alliance, and the sample that I took on the Conasauga is that giant red dot in northwest Georgia. So depending on what we looked for, we were typically in the top 3 for any measurement of any of the PFAS that we measured in this study. That heat, the size of the dot, is the overall concentration of PFAS that we had in our sample. So before this study, I was aware that this was an issue and we were already working on it. When Waterkeeper Alliance sent me a screen grab of this map from the report before they released it, they were like, what is going on? I was like, well, I'll tell you what's going on. There's a lot of carpet in the region. It's not all in Dalton, but there's a lot of carpet in Dalton. And that has left an incredible legacy that we have to come to terms with. So locally, I'll use this as a case study. Rome is one of many municipalities that has sued a bunch of companies to try and address its contaminated drinking water. So in 2016, after those original health advisories were listed, Rome found that its drinking water was above those thresholds. Rome, the city of Three Rivers, is very fortunate to have another source of water, the Etowah, which does not currently have high levels of PFAS in it. So Rome was able to switch its source over primarily to the Etowah. Well, the Etowah intake is kind of a brick shed compared to the giant 3-story building that they were using to pump water out of the Oostanala. It was only ever meant to be an emergency backup. So the city started doing some research to find out how they could go about treating the Oostanala so that they could use it again. They started with granular activated carbon. This is essentially industrial scale Brita filter, right? While it is effective at moving PFAS, it's not as reliable. So if we are looking into the future at essentially we can't find any in the sample to pass EPA's proposed MCL, the granular activated carbon, the GAC system, wasn't that consistent. It was also very maintenance heavy. And so in 2019, the city of Rome filed a lawsuit. And in 2022, they approved a truly eye-watering $100 million new drinking water plant. This was before they had even made it to a courtroom. Ratepayers, their bills started going up immediately. And this was because for Rome to have a future, they had to return to the Oostanala as their primary drinking water source. And reverse osmosis was the only technology that currently exists that can do that at a scale, at that kind of scale. Earlier this year, they did reach a settlement agreement with a bunch of the companies to currently, it will be more than this, but currently a sum of $159 million. But again, when we think about the cost for a city the size of Rome, that is not a large city. And when we think about, again, how these contaminants have spread so far and wide, when we start to think about, I think that that's really sobering to think about the financial investment that we're going to have to undertake to remove these from our drinking water. And so that's this is kind of represents the second fork of the motivation for companies to get out of this as quickly as possible, and that is liability. Rome had a winning suit, and so does every other municipality that is downstream of a facility that was using chemicals from DuPont and Chemours and 3M. And so that's why those companies are setting up funds worth of billions and billions of dollars specifically to settle lawsuits that will pay for people to either switch their drinking water source or treat it. And then I wanted to show something local, specifically here to Bartow. The Etowah, as I mentioned, is a source that is clean. There is one municipal system in Bartow that does have PFAS, and that is in White. Both well 1 and well 2 at that plant I think that's the one that's on School. Both of those plants recorded levels specifically of PFOA that were hot. I think it's 33 parts per trillion on this one and 27 on the other. This is a screen grab from EPDs Story Map. So if you want to kind of do a deep dive on what the state has collected so far, The Environmental Protection Division has created a story map where you can look at all that data. White was recognized as one of the municipalities that needed help, and they were actually funneled a fair amount of money from the federal government to tackle this. GIFA awarded them the money to do it, and they put it out to bid late last year, where they are going to either consider, as I mentioned, switching the source of their water away from those wells or building a facility that can reliably produce drinking water with zero PFAS contaminants. And that's kind of the local update for Bartow. The broader impact, why we all should care, is the way this moves forward is going to impact our tax burden. It's going to impact how these facilities are built in the future, and it's not always beneficial. There it is. When we go back and look at Rome's solution, sorry, right here, reverse osmosis, this is the best solution out of a lot of bad solutions, but so reverse osmosis as a technology is extremely power hungry, so it's going to be expensive for them to run, so it's a good thing that they got more money than just the cost of building it, because they're going to have a much higher utility bill to run this plant. Beyond that, reverse osmosis is so effective at removing things from water that it can actually make water less healthy for us. So there are lots of minerals in the water that we need, and our drinking water is our primary source for how we get them in our bodies. Reverse osmosis removes those minerals and then has to be synthetically added on the back end, or like human added on the back end, so that our drinking water meets those mineral needs. So again, as we think about the long-term impact of this emerging contaminant, it is broad and it's very far-reaching. Now, there is a lot of exciting developments. As I said, all of these economic drivers for these companies are pushing them to put a lot of money into research and development in two separate fields. So you've got reformulation. It's finding how do we create this product without using PFAS. They've been pretty successful in doing that with firefighting foam. So an individual in Australia developed a PFAS-free firefighting foam that meets kind of aviation standards for how quickly it will put out a fuel fire. That's exciting. Less promising is for a lot of the textile applications. So essentially every outdoor gear company has some team that is working on this, and they're having a really hard time creating waterproof textiles without PFAS. It's really difficult. There are lots of things on the market. They're not as durable. So a lot of companies, you'll see PFAS-free labels on their lower and mid-tier offerings, and their highest performance gear can't meet those standards yet, so they're still using PFAS. Patagonia is among them. And for all of the good that Patagonia does, they also reference this, how much work they're putting into it. They're very transparent about the work that they're having to put in to try and transition away, and also admitting that they're not there yet. So all of this research and development is helping that reformulation. It's also helping environmental scale removal. So there have been breakthroughs. One grad school student discovered a way that breaks one type of PFAS down using very little energy, low temperature, and pretty common lab solvents. That's an enormous breakthrough, because the energy required to break that alkyl-fluorine bond typically is very immense. So you're looking at incineration if you want to break it down. So that's exciting. There have been some developments about creating biota. So the kind of conventional methods that we treat wastewater now is using good bugs to eat the pollutants. They're finding strains that could potentially serve that purpose for PFAS. So there's a lot of research that's going on. I don't tend to read too much into one or the other until somebody can demonstrate its performance. Up in the Great Lakes, they're also using bubblers to bring the PFAS to the surface, to that kind of film at the surface, and then scooping it off that way as a way of like processing a lot of water and removing the contaminated, small amounts of contaminated water. So there's exciting things that are being developed that I hope will help us address this problem at a large scale. And in the meantime, CRBI is here doing the work we do to help raise education. We very rarely get involved in enforcement actions. We did earlier this year with a manufacturer in Tryon, and sat at the negotiating table for months and came up with an agreement where they agreed to stop using any PFAS by the end of this year. That's a really exciting outcome for us. We want to see more and more companies pivoting away from the use of these chemicals to begin with. And if we can't get there, we want to see them stopped at the source. Stop sending these things to wastewater treatment plants that cannot process them. So I believe that is all I want to open it up to questions. I believe they want folks to get to the mic if you can, so that your voice will be captured in the recording, but I'm happy to answer some questions.
All right. Here you go.
My question addresses RO, reverse osmosis, reject water. Will that not produce a higher concentration in the reject water of the PFAS? And what are you going to do with that reject water, and how are you going to handle the PFAS in it?
So the design plans for that facility in Rome are not completed. I would guess that they're somewhere around 40 to 50% done. That will be a part of the plan. Typically, when these systems are developed, that wastewater is separated and containerized. The goal is to get it as concentrated as possible and send it to a permitted facility for incineration. That's not a perfect solution. Again, this is where we're looking at those future technologies that will come online and with less energy help break down those bonds, but currently that's typically how that's handled.
I was just wondering if there are any known bacteria or enzymes, bacterially produced enzymes or other natural substances or organisms actually that can break down PFASs?
There is some promising research. I want to say it's out of New Mexico. I could be completely wrong on that. I believe that there was a facility in New Mexico that was looking at that specifically. Again, the goal of finding a way to use our conventional methods with new biota to break those things down. I've seen a couple of relatively promising white papers. But again, the dilemma is how much faith do you put in any of that until you can show it on an industrial scale? And scaling is always what's hard. The fortunate thing is this is a problem that is forefront of mind for the federal government. So a lot of money is going into this. Not nearly enough, but a lot. It's kind of a little bit of both. So they don't have enough money to fix it for everybody, but there's more going into the solutions than we've ever seen by a long shot. And it's helping fuel that kind of research.
Sorry. So for the average consumer, where it seems that these chemicals are all over my house, from dental floss to any non-stick cooking foil, surface, raincoats, hiking boots, I mean, what can the consumer do to help with this problem, as far as, I guess, how to be educated about purchasing things?
Yeah, I think I have long ago ditched non-stick pans, and I just scrub now. A lot of times these chemicals end up in the environment at the site of manufacturing. It's because of wastewater from manufacturing processes. So it's not like if you're wearing a Merrill jacket or you've got Gore-Tex shoes, you're just walking around shedding PFAS everywhere. Now, could you be shedding some? Probably. But the main way that these chemicals are getting into our environment is because of the manufacturing process and because of wastewater treatment plants' inability to sequester them. So anytime that you have alternatives that are PFAS-free, you're promoting an economy that rewards developing alternatives. So that's my recommendation, is if you're going to spend money on something, use your purchasing power to support an economy that moves away from those chemicals. The other thing that you can do for your own family safety is, again, I mentioned granular activated carbon can work. If you suspect that, or you live in Rome and you know that these can be in your drinking water, having a Brita filter at mine should give you some peace of mind. It's not a perfect technology, as I mentioned. It's something where the push to get you to change the filters is not just a gimmick. Granular activated carbon works a lot like a fly strip. So if you can picture like a fly strip hanging up over some like dive barbecue restaurant in Texas, it's just like flapping in the wind. It's been there for 2 decades. It's not doing anything. Everything that was sticky grabbed something 2 decades ago, right? Think about your Brita filters the same way. If it is sluggish as it's pouring out, that water is going straight through that filter, and the filter is not grabbing anything. Because the granular activated carbon, that activated carbon is sticky. It's got these pores where it grabs holds of stuff and keeps it. But once all of those sticky spots are used up, it's not doing anything. And so on an industrial application, on a large-scale application, it's impossible for the city of Rome to know when that GAC is going to be spent. So that's why they had some results where this month we got a hit of 6 parts per trillion, 7 parts per trillion when we were getting 0. It's because they don't know exactly when that's going to happen. But if you want to find a consumer-grade way to protect your family, a Brita filter, a carbon filter in your refrigerator works just fine as long as you maintain those filters.
Hi, my name is Helen. I'm a resident here in Bartow County. My question is a little more whereas policy, local government intersects with this issue. Is our local government helping you guys? I mean, what is in Bartow County? Do you have any knowledge of what our local government is doing to address these issues? I have small children who live here. They go to the city school, so I have a very vested interest in figuring out what they're doing about this.
Right, well, I would say a couple of things. The drinking water professionals take this issue very seriously. I would say the greatest interactions that I've had have been with the city of Rome because of the level of contamination they're dealing with there. And they have worked tirelessly to adapt, to reconfigure their plant, to figure out if they can make GAC work. On the local level, there is a lot of drive to find solutions because nobody wants to be the local official where you're answering to your neighbors next door, questions about what's in their water. They take it very seriously. Beyond that, I don't think that there is a lot of hope for Georgia to start passing anything, strict anytime soon, because Georgia generally has a tendency to wait behind EPA. So they're not going to get out in front of what the federal government is doing. And, there may be a little bit of sense to that. Of course, I might wish that they would be, promoting, the health of the public health and our drinking water resources, even in advance of EPA. But EPA has a lot of resources to study these things. So they typically stand and wait behind, and they won't, the legislature, the General Assembly is not going to touch anything on a sweeping scale until EPA makes its decisions. So hopeful news on the local scale, maybe less hopeful news on the state scale. Maybe one day that'll change.
All right, here I come. Another question.
So as a consumer then, how do I tell in my drinking water how much PFAS there is? I mean, how do I know how clean my drinking water actually is?
So there are some databases that you can look at. Again, that EPD Story Map essentially has all of the data. Excuse me. That story map has all of the data that the state has collected so far. And so, you know, you can look, Bartow's, like kind of central Bartow, Cartersville's main drinking water sources came back, you know, below reportable levels. If you are on a private well and you don't know what the history of the land use has been around you, there are some companies that can send you an at-home kit. They're not completely cheap, but they're not overwhelmingly expensive either. There's one company that we're actually in a partnership right now to do broad spectrum surface water testing across the basin. But those kits, I want to say, come down to like $70 a piece. They'll ship it to your house with a return label, and it's just as simple as filling a cup and let it sit on your counter for about 30 minutes as it drips into whatever waste container, an empty Gatorade bottle. And then you take that cup, put it back in the box without any water, and send it back to their lab. And they have a filtration media that they sell commercially as like an add-on to Brita called Dexor, but they use it in that test kit. Based on their white papers, it's every bit effective as any other test method, if not quite as analytical as some of the other labs. Cyclopure. Theirs is essentially identical to EPA methods. So there, it's down to around 3 or 4 parts per trillion is about as accurate as it's going to get.
What about the commercially available home filter units that you can buy that you pour the salt crystals in? And I'm not really sure all the things it filters out, is that effective at all in this case?
You know, that's a question that I probably ought to do more research on. I haven't done a lot because, to me, whole home filtration is not something that's financially accessible to most in the community. And so it's not something that I've given a lot of consideration to because of that cost hurdle. I would suspect that given some of the technologies that they use, there are some of them probably handling it better than others. Not all whole home filter systems are made alike. So that'll be an interesting thing for me to go. I've got some homework.
Hi. So you mentioned the health concerns and the effects that it has on humans, but how is it affecting like our endemic species? I know you touched on that at the beginning. So what are some of the effects that you're seeing on those, and are any of those species like keystone species that we should really be worried about seeing the extinction and or health damage to?
So the impact is negative. In freshwater systems, there's not been as much research about the interactions in, say, fish. That body of evidence is growing. But essentially, all of those health outcomes that we see increase on a community scale also happen to aquatic species. So you see liver issues, you see reduced immune response. So a lot of times when you have an environmental contaminant like that, it's really hard to point at PFAS as the culprit. But if you see an increase in the instance of fish kills, if you go and do a biopsy of a dead fish, it's typically going to tell you it's columnaris. It's some bacteria that fish's immune system should have fought off naturally, but it was weakened to the point where the infection killed it. And so things that reduce the immune response have an impact. And so I don't think that, again, we're talking about subtly increasing those levels on a community scale. So it's negative for everything, but you don't typically see that acute, this particular fish that's really important is super heavily impacted by PFAS. Everything is made a little worse. There's a lot more research on coastal environments because of seafood industry than there is freshwater, but like I said, that evidence is growing. But it's not usually good news anywhere we look at PFAS.
All right. Well, Jesse, thank you so much for being with us tonight. And once again, everybody, thank you for coming out. Please, if you haven't already had it, well, on your way out, there are some surveys. We would love to get your feedback on tonight's lecture and then our events that are like this in general. And also, if maybe not with this crowd, but if y'all want to go play in my big backyard, the exhibit that's in there is closing after Labor Day weekend. So this is one of your last opportunities to check that out. All right, thank you guys so much. Jesse, thank you.
Yeah, and I did just want to point out, I threw my contact information up here. If you have more burning questions that wake you up in the middle of the night, feel free to reach out. Or if you're curious about the other things, this is one very small fraction of all the things that CRBI gets up to, and I would love to talk about our restoration projects, which are a lot more fun.